Hello, so this will be our group's presentation for our term report for ECE 1150, Intro to Computer Networks, and our group's report is on the evolution of ZigBee's benefits for Internet of Things applications and wireless personal area networks. And then you can see our group members right there. So, a little bit, first we're going to cover what is ZigBee. Alright, so ZigBee is going to be an IEEE standard for communications, and it is an especially effective standard among Internet of Things or IoT devices. And it has many advantages within the IoT space that other sorts of IEEE standards don't have. Advantages like optimized throughput, minimized error rate, low cost, and low complexity. And we'll cover each of those a little bit later on, but just a little bit more background first. So the ZigBee standard was created around 2004 and has been, kind of built up and upgraded over time. But it was named ZigBee after these sort of zigzag dances that honeybees, used to communicate. So this style of communication the honeybees do is a great parallel to the way that information is kind of shared within a ZigBee network, within the mesh and the topology of everything. So that's just some background there. But now we're going to cover some advantages of ZigBee. So ZigBee holds a few advantages over different IEEE standards like Wi-Fi and Bluetooth. For Internet of Things implementations, Wi-Fi and Bluetooth are just not the best choice that you can make. Wi-Fi and Bluetooth struggle with issues like power consumption, complexity, and also cost being a big one there. Compared to these networks, Bluetooth and Wi-Fi, ZigBee is a much more flexible, much less complex, and much less power-hungry network. ZigBee also has a few advantages as far as connectivity and topology that Wi-Fi and Bluetooth don't have. These things make ZigBee much more suitable for these kind of IoT applications. Of course, ZigBee is not perfect, and like all things, it does have its limitations.
Although we have learned that using the ZigBee standard in wireless personal area networks has many advantages, we would also like to touch on some of the disadvantages and open issues that still exist with ZigBee. These issues can be broken up into two main categories: scalability problems and noise susceptibility. The ZigBee networks have scalability problems because although they can be scaled up to thousands and thousands of nodes, as we add more nodes, the algorithms that control transmission and selection of nodes during transmission actually begin to slow. The algorithms are unable to keep up with the amount of nodes in the network, and latency will increase and throughput will decrease. In terms of noise susceptibility, on the other hand, even something as small as a microwave oven can affect a ZigBee network. But the most common noise interference that happens with ZigBee networks is from nearby Wi-Fi networks. A possible solution to the Wi-Fi networks being within range is to use different frequency bands for the two networks, but from our research, we couldn't really find any solutions to the microwave oven problem.
So our first simulation will be done in MATLAB, and we have simulated a text messaging interface that will give the user what the message will look like before the transmission and after the transmission. The message, which is represented in character arrays, is first converted to a digital signals, which is represented by binary arrays in MATLAB. And then this binary arrays will be modulated either by ZigBee or Bluetooth protocols into analog signal that are ready to be transmitted to the channel. Through the transmission, the signal will experience a white Gaussian noise. And then after that, the analog signal will be contaminated. And then the demodulator from ZigBee or Bluetooth will try to convert it back to the digital signals, which is again represented in binary arrays, and then convert it back to the text message. We will be experiencing some sort of contamination in the text message. So opening our code, we have provided the messaging simulation interface as part 1. So we want to clear up everything before we run the simulation. And we have to make sure the part 0 is initialized, otherwise you will get an error. You can customize the text message you want to send over here, and also change the value of signal to noise ratio over here. For example, we'll be using -5.0 as signal to noise ratio, and we'll be using ZigBee OQPSK protocol to transmit. We are able to see with this signal to noise ratio, the text message is pretty much all contaminated. It's not recognizable at all. But if we increase the signal to noise ratio to, for example, a higher value, for example, 2.0, we're able to see the text message is recovered without any error. For the second part of the simulation, we're trying to compare the bit error rate in both ZigBee and Bluetooth. So you're able to customize your own signal to noise ratio interval. So we'll be testing from -5 to 5 with an interval of 1 with the simple text message over here. So the content of this text message shouldn't really matter since this is only used to calculate the bit error rate. And then we'll be transmitting this text message with a trial number of 2. You can customize the trial numbers here. The higher number of trials, so the smoother the curve is going to look like. However, the process might take a little bit longer depending on your machine. So we'll be using a trial number of 2. And let's run the simulation. We have not initialized part 0. So let's run part 0. And then run part 2 again. Those 4 arrays will be representing the bit error rate. For example, here, this represents when the signal to noise ratio is -5 with the protocol of ZigBee BPSK. And the second one is for the signal to noise ratio -4, -3, -2, etc. And the second row is for a different protocol, which is GFSK, and the third row is going to be OQPSK, and the last row is going to be representing the Bluetooth low energy. And we're able to see the Bluetooth low energy has a significantly higher signal to noise bit error rate, compared to the ZigBee. Although there are small intervals of signal to noise ratio where the Bluetooth low energy might have slightly lower bit error rate. After I have increased the number of trials to 10 and also the new signal to noise ratio range between -20 to 20 with the interval of 0.05, we're able to monitor the curve in a much smoother way. We can see that the Bluetooth low energy has a much higher bit error rate, no matter the signal to noise ratio. And also, the ZigBee, different ZigBee sub-protocols will have a slightly different bit error rate. But their average, which is indicated in the green line, is significantly lower than the Bluetooth low energy, which is indicated in the purple line. We have also included a simple hardware simulation where I have purchased 2 ZigBee modules that are directly connected to my personal computer. And they'll be connected through the UART, through the COM ports. And the data through the COM port will be monitored by the XCTU application. So we'll be trying to send the data packets between those 2 XB modules, and we're able to monitor the throughput directly on the XCTU software. After we set it up the hardware circuit, we can start sending packets in the software XCTU and monitor real-time the throughput. The throughput is about 2.4 to 2.5 kilobytes per second, with the highest transfer ratio of 2.65 kilobits per second. Right now it's about 2.56, but 2.65 is happening around here. However, we are able to see that although the ZigBee is having a lower transmission speed, its bit error rate is significantly lower than the Bluetooth. So in a scenario where the bit error rate is a significant factor, ZigBee is definitely a better choice than Bluetooth.